Okay, everyone. Thank you for coming to this talk. I think it's 5:40 now, so we can begin. My name is Furmanek, and for the next 60 minutes, we are going to talk a little bit about basic designs and the things, how we broke them in the software engineering, in software design, in programming languages, in platforms, be it .NET or whatever else. We are going to see how things are broken, why they are broken, and we are going to sometimes dive deep into like technical details, sometimes go through like solid principles, etc., etc. But before we begin, there is one important caveat here. After this talk, you are not going to change how you do stuff. This is the important part. I'm not trying to convince you to do things differently. I'm not trying to explain that things are broken and from tomorrow you implement your code differently. Nothing of that sort. Actually, during this talk, I will show you and I'll try to convince you that some of the things that you believed are wrong, and then I will ask you to continue believing in those wrong things. So pay attention to those. But anyway, we are not going to change how we do stuff. We are just going to understand why those things look the way they do, and we are going to understand why they are broken. That's it. Couple of words about myself. I'm a software engineer with something like 15 years of experience now, ranging from big tech and startups from various domains, etc., etc. Blogger, public speaker, drop me a line on email, Twitter. I also wrote those two books, one about maths, the other one about .NET. Visit my blog at blog.adamfurmanek.pl, and let's move on. Agenda for today. So we are going to bash various principles in the programming world. We'll start with solid, especially with Liskov substitution principle. Hands up if you ever heard about this principle. Lovely. Hands up if you know how you broke it last week. Oh, there is one. There is one. Oh, okay, another one. Lovely. So we are going to see why Liskov substitution principle actually applies to the enterprise world, even though we typically explain it with fruits or rectangles or other stuff that looks nice when we talk about inheritance, but actually is completely weird when we talk about the enterprise-ready code. Then we'll go through other principles like dependency, inversion, inheritance, exceptions, etc., etc. We probably won't do all of that because this talk is planned for something like 90 minutes. So we'll do as much as possible and the rest will remain on slides. So the very first thing, Liskov substitution principle. Think to yourself for a couple of seconds how you would explain this principle to a 5-year-old, and then how you would explain where we can break Liskov substitution principle in the enterprise code that we break every day. And in order to understand how to do that, we need to go back to basics. And Liskov substitution principle is actually pretty old and pretty new at the same time. It's part of solid principles, as we call them nowadays, but it comes from 1994, from the paper that you can find on the internet. Actually, computer science is great because we can easily read all the papers that build the foundation of our industry. It's not the same as with mathematicians. It's hard to talk, to Newton, Leibniz, etc., etc. But with computer science, you can still meet these people that put those, grounds in the computer science. And if you look for the paper up in 1994, you'll find it the same thingy that you have on the right side of the screen, right? So it is available, we can take it, and it's important to understand why we even have Liskov substitution principle, right? It's not like law of aerodynamics or whatever. It's not something that we found out, it just is in the world. No, the paper says that they want to take position and explain how they believe it's good to implement the software. They simply say something, hey, we believe this is what we should be doing. So you may agree with them and disagree at the same time. It's just that we decided to agree because we felt like, okay, that makes sense what they say. And what they say is that they want to ensure that whenever we have a supertype and we can tell something about the supertype, then objects of the subtype should meet exactly the same. That's the idea. So what they are trying to say is, if we have inheritance, there is a base class and the base class does this or that, then it's cool if the inheritance, like the child class, does exactly the same. This is cool, right? So let's go through this example and let's understand why we are taught this principle wrong, or actually in a very misleading way. If you ever go to Wikipedia and look for Liskov substitution principle, or if you took like a course at uni, typical example explaining Liskov substitution principle is with squares and rectangles. So the idea here is that we basically have a square class that derives from rectangle. Now the thing is, if we try to use the square in place where we expect rectangle, it might be a little bit misleading because square expects that both sides are always equal, right? That's a good definition of square. But rectangle doesn't have this requirement, right? So now when we try to write a method that accepts a parameter of type rectangle, and then we call some setter on this rectangle, like set first side, then the other side will change at the same time because we want to have both of the sides equal, right? And now we claim or we suggest that this breaks LSP. Why? Because rectangle allowed us to set those sides to different values, but square doesn't let us to do so, right? We take it for granted. This is how it's explained in Wikipedia. It does make sense, right? So let's take a different example. What about ratio maintaining component? Imagine that we are writing a widely popular framework for UI applications. We call it short WPF. And in this WPF, we would like to implement a component that keeps like the ratio of the image, meaning that if we make it taller, it also needs to become wider, okay? Because we maintain the ratio. Obviously, as with all the framework, all the desktop frameworks, we typically have something like base class, base interface, component, pane, whatever, that we can put on the Canva. And then we inherit from it or we implement this interface now, okay? So now I ask the question, if we implement a component that I called here, what did I call it? Fixed image, that tries to maintain the ratio. If I implement such a component and if I change one side of this image and I need to maintain the ratio, so I need to change the other side at the same time, does it break LSP? Quick roll of hands. Do you think it does break LSP? Hands up. Okay, a couple of those. Who thinks it doesn't break LSP? And who has no idea what is this about? Okay, gotcha. So the thing is, I am referring to this example of square and rectangle because it's a common example and you may have heard about it. The idea here is we have setters for two sides of rectangle, set width, set height, right? And now those setters are independent. But then we inherit with square class. And square class, when you call set width, it needs to adjust the other side at the same time. And the opposite, right? So we claim this breaks the LSP, and this is what Wikipedia claims. And this is actually what others claim as well, like Uncle Bob Martin. However, if we now think, okay, how would I implement a ratio-preserving component? I need to have this behavior. I change one side, the other side changes as well. So if it breaks LSP, and we know LSP is cool because it's part of solid principles, so it's mantra for our programming day-to-day activities, right? So we can't break it. So how do I implement this stuff? And if it doesn't break LSP, then why does this? And the answer to that is this doesn't break LSP. And the example on Wikipedia is completely wrong. But we need to understand the paper carefully. So if we take a look at the paper and we take a look at how LSP is defined, we see that they are using mathematical notion to say that there is a subtype requirement. They propose, they think it's cool to have subtype requirement preserved in our software engineering. So if phi of x is some property provable about the objects x of type t, then it's cool if phi of y for objects of the subtype is preserved as well. In other words, we have a property that we can prove for the base type, okay? And then we would like the same property, we would like to be able to prove it for the subtype, for the type that we inherit from with, right? So this is the idea. Now the question is, what is phi in this definition? Because if we allow phi to be more or less anything, then I can go to something like that. How about I have a base type with virtual method foo, with console writeline literal, and I claim my phi is that intermediate language implementation for this method is this. And I expect this phi to be preserved for every single subclass inheriting from this base type. If I am allowed to do so, then what effectively happens is we don't have any polymorphism anymore, right? Because I claim that I am able to prove that the intermediate language of the base type method foo is this. Therefore, I should be able to prove the same for the subtype, right? But it doesn't make any sense, right? So if we read the paper in this way, then LSP is useless, just to say, right? Whatever we are talking about in LSP is about the contract. So the contract here is what dictates what properties we can consider for LSP. The contract is something that we need to pay attention to, and what's more important, and it's in red on in this slide, is that it's explicit. It must be an explicit contract, so it must be stated carefully and explicitly somewhere. So according to Wikipedia, and notice that actually this is from 1986, so 8 years before LSP. So when they were writing the LSP paper, they already knew about the contract. So the contract is something that is here, that is provided, that is formal, precise, and verifiable, meaning that we can't just wave our hands. It must be something that is very concrete. So now going back to square and rectangle revisited, and I encourage you to take a look at like the LSP article on Wikipedia, just to make sure what's going on over there. So according to Wikipedia, we have the base class rectangle, we have square that inherits from rectangle, and when we call a setter on square, it modifies two sides, this breaks LSP. And this is wrong, because we never said that we are not allowed to modify both sides with one setter call. That is the important distinction. We never said this is our property that we want to preserve. And properties as contracts, they must be explicit, and they cannot be just, you know, hand-waving just like that. So now, having that in mind, think about when did you break LSP in your enterprise code recently? And the thing for that is we need to look for contracts that are explicit, precise, formal, and verifiable. And the problem is those constructs are not only in the source code. That is actually the worst part of LSP and everything else, and you know that stuff, right? When we have contract in the source code, it's super cool because most of the times the compiler takes care of proving that we didn't break it, right? We have the typing system, we have things like number of parameters, assuming we write in some decent language, right? Because if you go to Python, JavaScript, whatever, you don't even have the type system, right? .NET is actually a little bit more civilized in here, so we can rely on those things, but at the same time, .NET is still very weak. For instance, think about how would you implement a method that proves that has this contract, that it accepts a list of integers, and that list must not be empty. Or we can make it even crazier, like the list must have at least 5 elements. How do you implement something like that in C#? Well, you probably would need to go to runtime checks and throw exception, right? So there's no security and no safety at all. However, there are languages that let you define that. For instance, Idris in one of them. So if you really want to have like language that really takes care of proving all the contracts you can think of, there are more powerful languages than C#. So take a look at Idris or anything that is kind of ML-based and Haskell-based. But anyway, we need to have contracts that then they can be anywhere. They can be in wikis, in documentation, they can be decided over the phone with our clients or whatever, and we need to make sure that we don't break them. And this is the hard part of LSP. We don't necessarily know where those contracts are, and it's easy to break them if we don't pay attention to them because compiler can't protect us from that. So the idea how we break the LSP in the enterprise world is on the slide now. So let's go through a really quick example showing how we break the LSP in the real life. And this is actually a problem that I found over 2 weeks in like 5 different projects in my company. So I kind of guess it might have happened in your case as well. So what do we have here? When do I have my Morse pointer? There it is. So we have a method. The business context is, imagine that we would like to download files from the internet from, let's call it S3 bucket. And we have like a geo-redundant storage, okay? So we try to download files from Copenhagen data center. If this Copenhagen data center is down for whatever reason, we go to Berlin data center, right? So we have main connection, and we have backup optional connection that we use if and only if the main one breaks, right? Or we can even do load balancing, round robin between those two connections or whatever. So we have a method that is basically provided by the third-party library, so like helper method or whatever, that takes those two clients and then it takes the lambda what we want to do with these clients, right? So the lambda would be basically client download file, async or whatever else, right? So we have this method, it has some implementation that we actually don't care about here. The only thing that we do care about here is there is this method, doInternal, that first tries to call this lambda using the first client, main connection to Copenhagen. And if it fails and throws the exception, then we try to call the other client. So we go to Berlin or whatever else, right? Now, how do we use this? Well, we use this in this way that we have our code. This is actually our business logic in here. So we try to download the first file, the second file, the third file, and then we concatenate them or whatever, right? How would we unit test something like this? So think about that for a second, what the unit test would look like, and you may come to something like this. How about we just call this method, we pass a throwing client, so client that always throws the exception, always fails, and then we have working client that always succeeds, right? And then we just check whether we have some expected literal or whatever else, right? We run this code, we test it with unit test, it's all green, we deploy to production, it's perfect, and then people start complaining. Why do they complain? Gosh, because we download files one by one, okay? We download them serially. And here comes the part where we start breaking LSP, because what do we do to make this faster? Ideas. Parallelize that, exactly. And we have C#, we have async. How about we turn that to async? Notice that someone was actually pretty smart here. They just implemented the interface. So we just need to change this interface to start returning something like task of string, completable future of string, promise of string, or whatever. We implement a different client that is now returning this promise of t. And then we do something like first wait for result in C# that would be await first plus await second plus await third, right? We run the unit tests, they are all green, we deploy to production, and then everything fails. It doesn't work anymore. Where did I break LSP? This is actually, as I said, this happened 5 times over 2 weeks in 5 different projects. And imagine that if you were given such a task like that, you would probably give it to a junior developer on your team because it's just put task over there, async aware, and that's it, right? Where do we break the LSP? We break the LSP in this part, actually in this line of code. Why? Because I said, and you may have missed that because I am speaking pretty fast, I said that the contract of this is if this fails and throws the exception, then the other client is used, okay? Where does it throw the exception? It doesn't throw exception anymore in the downloading part. It will capture the exception, put it on the task object, and propagate when you do task result or await task or whatever else, right? So this exception is not propagated in this line anymore. So we are not catching it here. We are never calling this line of code. So this is how we break LSP. And the contract here is not something that you can easily put in your code. It's not something that you can verify in the compiler. And what's worse, if you were to verify this contract with unit tests, you would need to implement a unit test like this, that you prepare the failing conditions for the client, which means it could be, hey, client, go to the internet and use non-existing DNS or whatever, and then you verify that it does throw the exception. This is how you need to verify the LSP. So the hard part about LSP is that contracts must be explicit, and sometimes it's super hard to verify them. And I also mentioned that LSP, or the contracts for LSP, can be put in many places. Source code, wikis, documentation, yada, yada. If you go to Java, let's bash Java for a bit, right? If you go to Java and you check collection add in Java, you will quickly realize that this thingy can throw unsupported operation exception. You would not expect that on your list, right? You have a list of strings, you call add on this list, and bang, unsupported operation exception, like you had just one job to do, right? And you don't support it. What's the point of that? The idea here is that we would like to be able to implement immutable collections. So collections that we can't modify. So we can't add or remove elements. What happens if we have add method on the interface and we really don't want that method to work? We just throw the exception, or we could pretend like it worked. That would be actually even worse. So it's actually good that they throw the exception, right? But now let's ask them, okay, why did you design this interface in this way? Because now we need to actually answer a very tricky question. We said that we would like to implement adding on a collection, but we would like to support immutable collections. What does it mean, immutable? So actually, there are two different definitions we could use for immutability. The first definition is we won't modify the collection, right? So you give us the collection, we consider it immutable, we won't modify it ever. It's much more like, from our perspective, this is read-only collection, right? But immutability could also be something different, like nobody ever modifies this collection, right? It's remained in this state forever and ever, and it's never modified, right? So generally, in the first case, in which we consider the collection immutable, it's easy to prove that we didn't break it, right? We just show that, hey, we didn't modify it, right? We can verify that with unit tests. We can use a sub-interface that doesn't have the add method, etc., etc. But how do we prove that no one ever can modify this collection? This is something that we can't prove in the computer science. So now when we talk about immutability for our collections, and this is again LSP because contract is the collection is immutable, right? We need to understand what we are talking about. And now let's start digging into, okay, what do people mean by immutable collections? So if you ask Java, this is the wall of text you get. And they explain why they put the add method on the interface and why they throw exceptions. So if you ever wanted to understand why the exception is thrown, this is the documentation. Have you ever read your documentation of add method on your list of T? No? List of T in C# copied from Java, they have exactly the same. List of T in C# can throw the exception on you for the same reasons as it's explained here. I encourage you to take a look at that. But hey, there are other languages running on JVM, for instance, Kotlin, for instance, Scala, and they decided to implement things differently. For instance, this is how Kotlin implements immutability. So you can see that we have iterable at the top, which is something like IEnumerable in our case. Then we have collection, then we have list, but at the same time we have mutable iterable, and finally we have mutable list that it inherits or kind of implements two interfaces. So mutable list is both list and mutable collection. So now if you receive an immutable collection in Kotlin, it's like it's read-only collection. You don't modify it because you never know whether you get a different implementation or actually you get implementation that lets others modify this collection, right? However, Scala took a completely different stance on that, and they designed two completely different inheritance classes. So in Scala, when you receive immutable collection, it comes from this thingy, so it never has any methods for adding or removing elements. But if you receive mutable collection, then it's kind of different class hierarchy, so you get completely different implementations. And then whenever you want to juggle between these two, you need to call to mutable and to immutable, etc., right? So when we talk about immutability, it's worth asking, okay, what does it mean? Because depending on the language, we get completely different thingies. That would be it about Liskov substitution principle. Let's bash another principle now, okay? So dependency inversion, another part of solid. We know that solid is single responsibility, open close, Liskov substitution, interface segregation, and dependency inversion. It's dependency inversion, not dependency injection. Sometimes people think that dependency injection is the principle. No, it's more of like implementation of the principle. So let's start with another thought experiment. How would you replace a string in C#? Let's say that we have system.string. We don't like it. It's too slow. It doesn't work. It doesn't support the things we would like it to support. How do we replace string with something else? And actually, before answering this question, we might consider, really, is it seriously someone would ever consider replacing a string in C#, right? So let's see what happened. Java improved their string implementation a couple of times. They have the same implementation of string as we do in .NET, or kind of very similar. However, around Java 9, they decided that it's a waste of memory to store strings as arrays of characters. If you know, character was supposed to implement UTF-16, but it doesn't, because UTF-16 is not 16 bits anymore, it's something like 21 bits, and character is 16 bits only, so we can't implement UTF-16 with character anymore, but that's minor thingy. However, we wanted to implement UTF-16 to hold all the strings we could think of, and that's why for most of the strings that we implement in our applications, which are like English-based, we waste a 1 byte for every character, right? Java decided, let's fix that. So they changed the implementation to use byte arrays instead of character arrays to save the memory. Another thingy is whenever you add two strings with the plus operator, they tell you don't do that, use something like string buffer and call the methods to append, yada, yada, right? However, the plus operator works just like that. It is typically compiled to these things, right? But they wanted to do it different because the translation to string builder append or string buffer append, etc., it's cool when we really add many strings. But when we just want to add, two short strings together, it's completely waste of memory and of time because we need to allocate this string buffer every single time. So they implemented it dynamically, so now depending on whatever you do in Java, you actually call an instruction that is called invoke dynamic. It's something like dynamic typing, etc., which gets compiled to a different implementation depending on which JVM you use. So this now can be changed in runtime if you upgrade JVM to another version. That's Java. What else? Facebook. They decided to implement their own string in C++, and they get something like 1 performance improvement, both in terms of speed and memory. So you may think to yourself, 1%, what's that, right? We probably spend months on replacing the string with something else, and we get 1% in return. But think about the scale. Facebook runs on literally millions of machines. If you now can cut 1% of those machines, imagine how much money and resources that is. And they did it by replacing the normal string with some other small string. You can actually find the talk on the internet explaining how they did it. So Java did it, C++ did it. Moving to something else, JavaScript, right? When we think about the typical case in JavaScript, everything is an object. We typically think object means a dictionary in the JavaScript's world, right? So basically key value pairs. But they have something like 5 different implementations of objects depending on what you do with objects, because arrays, strings, and everything else in JavaScript is an object. So now depending on the case you are dealing with, you have different implementation, and that happens dynamically and transparently behind the scenes. So now coming back to C#, how do we replace a string to gain similar benefits? And the answer is we cannot. That is because when we actually take a look at .NET, a string is a class. It's not an interface. We can't inherit from it. We can't provide different implementation of that. What's worse, in exposed on the intermediate language level, meaning that whenever we actually use strings in the intermediate language code, they are kind of first type citizen, meaning that they are so hardly encoded, so hard in the platform, in everything, in the instructions, literals, yada, yada, that we can't get rid of them. Not to mention that .NET is implemented in the native code, and they rely on the strings being just an arrays, so they take pointers and do black magic behind the scenes. So we can't replace the string, and we can't get any performance improvements. So this is how Microsoft decided to break dependency inversion. But we can take that further to many other examples. Date time now. How many times did you introduce an interface for date time now? Right? Why isn't there an interface? I mean, there is now, right? But it wasn't there for so many years. Environment exit. If you ever call environment exit, actually stop doing that. Introduce interface the same way, because it will kill your application and you have no idea why. There are even libraries provided by Microsoft. Hey, we broke dependency inversion, but no worries, there is a library for fixing that. Moz is just one example. PowerMock in Java, another example. Anything that is broken, we can fix by using yet another library. Okay, but let's take a different example. What would you say if you learned that Adam Furmanek created a new programming language, and function. In this programming language, we actually have colors in functions. So apart from function being static and instance, public, private, yada, yada, it's either green or red. And I need to define whether the function is green or red when I implement the function. And the tricky part here is, if you call green function from green function, all good. If you call red function from red function, all good. If you call green function from red one, we don't like it, but okay, let it be. If you call red function from green one, that's a big no-no. We don't like that in my language. What would you think about that? And does it resemble anything? Async, exactly right. So this is what we have with async. You now have functions of two different colors. So you have green and red, and you can't call async from non-async method because you know it's gonna be deadlocks. But it gets even further. We broke the principle once, why not breaking it another time? How about value task now? So we actually have 3 different colors in .NET language, or in C# language specifically. It's not .NET platform, it's C#. So we have 3 different colors, and we kinda shouldn't be calling those methods just like that freely. And this is what we have in our language. This is the mess that we created. Other languages copied that blindly, including Python, JavaScript, C++. Only Java decided to do it differently. They decided to go with green threads instead of async, and it's actually way better, and even .NET considered introducing green threads, but seems like they abandoned this idea for some time, but that's a digression. Okay, so we bashed yet another principle. How about we carry on with async, because it's so easy to bash async, and we now talk a little bit about do not repeat yourself, okay? How would you implement, because imagine that you would like to provide a method that is like both async and non-async, right? We would like to provide 2 flavors, why not? How would we implement that in C#? Well, imagine that we are, sorry for that, imagine that we are implementing file read all text. Right? How hard can it be file read all text? Well, we just take the stream reader and we just call read to end. That's it. This is how file read all text has been implemented for years. What do we do if we introduce file read all text async? Can we call this code from an async method? We can. It would work technically, but we don't like it because it misses the point of async. So what do? Well, this is the implementation of read all text async. So first, it is way longer, but the important part here is you can't just reuse the implementation. And if you were to return internal read all text async, you would like to implement it for value tasks, you would have third implementation because you can't reuse the implementation, right? So not to mention that this breaks so many things like single responsibility principle, because we just needed to re-implement the method depending on the return type, which shouldn't be the case because it's business logic or wrapping the result. But also we can't copy this code and we need to do it in a completely different way. So do not repeat yourself is broken in C# many times. Let us now move on to yet another topic, inheritance. And this is actually a great topic because I would like to start with a simple interview question. You may have heard that. Do we have multiple inheritance in C#? Hands up if you say no, we don't. Okay, hands up if you say yes, we do. Okay, hands up if you actually don't know now, so you probably might fail the interview if it was happening today. The typical answer is we don't, right? We have classes, and we can inherit from one class only, right? This is what we typically say. So we do not have multiple inheritance. So this is what we typically say, that we only have single inheritance in C#. But it's kind of tricky because we know we can implement multiple interfaces, but we do not inherit from interfaces, we implement interfaces. So that's the difference in naming, as we are going to see. Sometimes we can't even inherit at all. Structures cannot inherit from each other. Why? No reason. That was just a business decision. There is no technical limitation for making structures inherit from one another. It's just .NET or Microsoft team decided that we don't allow for that. So there is no multiple inheritance in C#, there is no in Java, or is there? So the problem with multiple inheritance, or actually multiple inheritance is like a feature of object-oriented programming typically, when we can say that we can inherit from multiple base classes, right? C++ supported that. That is like one of the most notable examples in here. When Java was implemented, they were sort of scared of implementing that in their language because of the diamond problem. And then C# inherited them from Java because C# was copying Java like crazy initially. So that's why we don't have multiple inheritance in C# because diamond problem. So what is a diamond problem? Diamond problem is when we have a base class A on this slide, from which we inherit with B and C, and then D inherits from both B and C. So if we now call something like D method from A or D field from A, then we actually don't know whether we should be going through this route via B when it comes to overrides, etc., or via C. It makes sense, right? We have the same thing and we just don't know which to pick from. We have two things, one coming from B, one coming from C. How do we choose? This is a real problem, right? Or is it a problem at all? And I'm going to show you that first. We have diamond problem in many places in C#. We already solved it in many places. What's more, we still have multiple inheritance, and actually we have new way of doing multiple inheritance in C#. Then I will show you the actual implementation of multiple inheritance, and then we'll ask again if there is multiple inheritance in C# or not. The important part is diamond problem as we see it, that we have one thing that is, or actually we have two things that are similar and we just don't know which one to pick. This is a problem that is prevalent in the computer science, in software engineering, and we solved it many times. Let's start with a very tiny example. Let's say that we have two interfaces, interface A and B. Both provide method void foo, as you can see in here. Then we have class C that implements both of those interfaces and implements method void foo. Is it going to work? C# riddle. Hands up if you think yes. Hands up if you think no. Okay, this is going to work. Why? It seems like we are having some naming collision, right? Is this foo coming from interface A or from interface B? And actually, this is going to work because our line of reasoning here is doesn't matter. Because it's the same for both A and B, right? It's the same signature. Nothing can explode here. Nothing should explode here. We let it go. So you may say there is no diamond problem at all in this case, okay? Let's take it a little bit further. Imagine that we have two methods, foo method accepting two integers, and then we have method foo accepting params of integers, so basically an array of integers. So you can now call it a.foo 1, 2. Is it going to work? Hands up. Is it going to fail? Hands up. Okay, which method is going to be called? One at the top or one at the bottom? The one at the top. Okay, you're doing it right. So the answer is yes, this is going to work. Even though this calls, like the way we call this method, could match both of these, we say that, yeah, this one has two parameters, the other one is actually, you know, obfuscating this with an array. It makes sense to call this one at the top, right? But notice, you actually now break the compatibility. Because if there is no method, if this method doesn't exist yet, and we implement this method, then this line of code is going to work, okay? And then in another version of our library, we introduce this method. This method, this call site will now start calling this one. So we broke the compatibility and compiler didn't, you know, say a word. No warning, nothing of that kind. Where can it happen? Many times, for instance, if you get logging libraries. Logging libraries, they need to be very generic, accepting any number of parameters, right? And then we would like to make logging libraries faster. So we introduce another method that is being called and optimizing this specific case. But now comes the tricky part. If you compile your caller with the new logging library, then you will be calling this method. If you deploy this to the production system without updating the logging library, it's going to crash in runtime because there is no method like this. And this is actually what happens many times in like legacy code or code that we migrate between versions. But you might say, okay, there is no diamond problem here because clearly here we have two parameters and here we have only one. So it's just, you know, code juggling. Let's take it a bit further. What about this case? So we have method foo that accepts the long parameter and another method foo that accepts double parameter. And we call it like this, foo123. Notice that 1, 2, 3 is not a long value. It's an integer. It's not a double value because it's an integer. Which method is going to be called? Do you think it's going to compile? Heads up if yes. Okay. Does it break? Hands up if no. Sorry. Hands up if yes, it breaks. Okay, which method is going to be called? One at the top or one at the bottom? I can see people hesitating. It's going to be the same. The method at the top is going to be called. That is because we say that integer is converted to long and it's way better than converting it to double. You may say this makes sense. You may argue this doesn't make sense. Again, we may have the problem with compatibility if this method doesn't exist and we introduce it later on. But okay, you may say there is no diamond problem here because, okay, integers should be longs, not doubles, right? So let's take it further. What about this case? We have the interface A that has method object foo, and then interface B that has method string foo, and we would like to implement it with public string foo. Does it compile or not? String is an object, isn't it? Should it compile? Well, it does compile in Java. It doesn't compile in C#. Why? Business decisions. We just decided it doesn't compile in C#, even though it should work. And it works in Java, but it doesn't work in C#. So now we have an example where we kind of diverge from our base language called Java, but we decided to make a different call. And you might say, okay, this is again not a diamond problem because we have different signatures. They're only similar. But let's take another case. What about default interface implementations? So we have interface A with method void foo that does some provides some implementation. We have B with another method void foo with some implementation. And then we create C and we call c.foo. Does it compile? Yes, hands up. No, hands up. Okay. The answer is it does not. How do we make it compile? What? Come again? Exactly right. If we specify the interface in this place, so we cast C to either interface A or interface B, and then we call foo, then it does compile, it does work. So you can implement two interfaces. Now you tell me, does it look different than multiple inheritance? And I'm trying to show you, obviously, through all those examples. Diamond problem is there, and we solved it many times in the programming language. There are many ways to solve the diamond problem. One of the ways is nobody picks. We simply ban the code that tries to access the same thing from two different paths, and we say, no, just reorganize your code so it never happens. So we effectively ban multiple inheritance. The other approach we can take is there is just one pick, so there is nothing to pick from, just like we had the interface with void foo method, right? Even though there were two interfaces, they were very similar, or actually the same, so there was no actual pick, so we don't need to be bothered. Or another thing is we just pick arbitrarily. Like the language designers, they decided that integers are long values, not doubles. They might have said, okay, you need to specify which method to call, right? They just decided integers are longs and it works. And ultimately, the one and only solution is we let the user pick, just like we have on this example. We don't know which method to call, but we decided not to ban multiple inheritance from the default interfaces, but we decided, okay, user, you're smart enough, go figure what to do with that. So this is how we decided with the diamond problems in C#. And now coming back to multiple inheritance. Depending on what we are talking about, there are actually many types of inheritance. Whenever we started talking about interface implementations, it is because Java was scared to have true inheritance, multiple inheritance in their language, right? So they were so scared, they decided to change naming. Inheritance is now from base class. Implementation is when we implement interfaces. But when we talk about types of inheritance, there are actually many of them. We can have interface or signature inheritance, implementation, state, identity, etc., etc. So signature inheritance is what we typically call interface implementation. So we have a set of method signatures that we incorporate into the class, into the subtype, right? So this is signature inheritance, and there is multiple signature inheritance in C# because we can inherit from multiple interfaces. They tell you there is no multiple inheritance, but there is multiple interface inheritance, if we call it this way. And this is actually code in, some theoretical book, let's put it this way. When we talk about implementation inheritance, it's when we actually get the implementation, so the method body. Not only the signature, but also the body of the method. And we do have multiple implementation inheritance in C# because we have default interface implementation. We can get method bodies from many base types. When it comes to state inheritance, so basically inheriting fields, then we don't have that in C#, but we can emulate that with default interface implementation. Nothing stops you from creating like a private static field in the interface. That would be a dictionary holding whatever you want, and then you have getters and setters. Actually, some languages do not even have fields at all. For instance, Scala, they don't have fields at all. They always change fields to getters and setters, right? So this is how you can pretend like you have multiple inheritance, but C# doesn't support that like by the book, let's call it this way. And finally, it's identity inheritance. So we can inherit the constructor. So basically something being a type. We can't implement that in C#. We do not have multiple identity inheritance. However, we can implement that in the hacky way. So let's see a little bit of code that we are going to examine here. What we have in this source code, let's make it slightly bigger. We have base class number 1 with some integer field, base class number 2 with some bytes, base class number 3 with doubles, and base class number 4 with strings, okay? What do we do next is we do some black magic trickery, just as we always do. What we create is we create a multiple inheritance object that inherits from all those base classes, base 1, 2, 3, and 4, okay? What we do next is we take the base, we take this object, we pretend that it's now base 1, and we assign it to a field of type base 1, and we start doing something with fields, printing the object address, etc., etc. We do the same with base 2, with base 3, with base 4, and whatnot, and let's see if this works. And you can see when I run this application, then you can see that object with multiple inheritance created is at this address, and then it's pretending that it's of this type, and you can see this address is the same in all the calls. Let's see the code again. In those methods, I pretend that the object is, this object is base 1. I initially printed the address of this object, and then I check the address of this base 1 object, and I get the type, sorry, it's multiple inheritance object here. It should be, it could be either base 2 or could be multiple inheritance object because, hey, this is the same object. And you can see that the type changes with every single call, but the address stays the same. So you can do this black magic in C#. Now coming back to slides, do you believe there is a multiple inheritance in C#? Hands up. There are some of you. Do not say that in the interviews, right? There is no multiple inheritance in C#, period, even though now you know. Moving forward, probably the last topic for today is exceptions. So now again, C# riddles. What happens with this piece of code? So let's say that we throw the exception, then we have finally, and then we throw another exception from finally, and we try to catch this exception here. What happens? Exception number 2. Okay, hands up if exception number 2. Let's start with this one. Okay, hands up if segmentation fault or other nasty thingy. Nobody here. Ah, there is one. Have you ever saw a CLR engine exception in .NET? Okay, many things ahead of you. Okay, anyway, the good answer here is yes, it's gonna be exception 2, but with all what I'm saying here with those exceptions, take it with a bit grain of salt because really it gets messy, and it will be messier with every slide. What happens here? We do have a try block, so we throw the exception. How does it work now? We start looking if there is any catch block around that. If there is none, no catch blocks at all, then there may be nothing, meaning that it may just die. .NET or specifically C# specification tells you that if you do not have try catch, then this finally may not be executed ever. And this is allowed by C#. This is what was happening in Mono implementation. This never happened in .NET Framework nor .NET Core, but I am not sure if it's gonna change one day. So beware, you always need to have try catch per the language specification. So we take a look at the code. Yes, there is a catch block. Let's start unwinding the stack. What do we do when unwinding the stack? We execute all the finally blocks, right? So we execute this finally block, and there is this exception 2 thrown, okay? What happens with exception 1? It's gone. It's gone. So you lost the exception. And this heavily depends on the language you're dealing with. So C# will lose the first exception. Python 2 should do the same. Python 3 should store the first exception, preserve it. Python is actually good in this case. That's very rare. And another thing is Java that depends on the exception type. So now the same piece of code will work completely differently in various languages that we are talking about. Okay, what to do next with this such an example? So we know probably that never do code like this one, never put try finally in try catch, or actually never throw in finally, but we can actually do something better. And sorry for this being so pixelated. But anyway, where does this, I mean this code, where do we spot this code in our programming language, in C#? Is there any case we would implement something like this? So imagine doing this thingy. So if you do using var resource equals new resource, behind the scenes, this is compiled to var resource equals new resource, and then we have try finally, if resource not equal to null, resource dispose. Okay? So if anything happens in here, like you throw the exception, then you call dispose. And what happens now if dispose throw? If this method thrown for whatever reason, then you lose the exception in here. Using is actually broken in C#, never use it, because you lose exceptions. And another thingy to notice here, if anything happens in this constructor, God forbid throwing exceptions in constructor, but remember, there are people who do domain-driven design, and then they do it in a way that they access databases from constructors. Yes, they do this thingy. Some of us love it because we should never create an entity in an inconsistent state. Some of us says, seriously, calling database in constructor, yet they do it. So the exception may be from here, and your using will never catch that. So you will never call dispose. The question is, should we call dispose on this thingy, right? That's yet another problem we need to solve. But anyway, how do we fix using? If you ever wanted to know how do we implement using the right way, the blessed way in C#, this is the shortest piece of code I ever came up with. So what we do is we store 2 exceptions at the beginning. We create the resource before try, just to maintain the same like contract. We do something, then we catch the exception, we preserve it, and then in finally, we check if the resource is not null. In that case, we just call dispose, and we try to catch another exception. And now we do the if logic here to understand whether it was just 1 exception or 2 of them, and we aggregate them together. You may notice yet another interesting thing. There is exception dispatch info capture throw. Why isn't this guy just using throw? Okay, someone raises their hand. What's that? That is exactly the right answer. So if you would like to rethrow the exception, imagine that you have a code like this, method throwing exception, just like that. If the exception is being thrown, then the question comes, how do we rethrow it here? If we try doing throw E, then we lose the call stack. You probably know that because it's common. By the way, how do you do that in Java? You do throw E. How do you do that in many other languages? You just do throw E. It's just C# that is so careful not to lose those exceptions, right? However, if you do throw E, that actually loses important piece of, sorry, not even throw E. You may, let's wait with that. You may use special instructions like throw.
So you just do throw colon, and it should throw the exception or rethrow the exception the right way. But if you try doing that, you will notice, especially if you use debugger behind the scenes, that you lose the information whether it was thrown in the first execution or in the second execution. You lose this architectural call stack of what is happening. Now it's even worse. Your C# code, if you just print this exception, will print different stack trace than your debugger is going to see. So your Visual Studio or WinDBG will report different call stack than the console will print to you. You can create new exception. So you would just do new exception and you would pass this E as a parameter to this thingy, right? That would work as well, but then you change the exception type. Okay, so we know that throw breaks the call stack. Throwing new exception may do even worse, break the ways we handle exceptions. Async may lose the state machine, that's another thingy. What can we do? Well, if we are old enough or born early enough and still working in .NET Framework, then there is some trickery with remoting behind the scenes. So you can actually serialize the exception for the remote call over COM interfaces and then rethrow it. Just don't do it. In now new C# starting with .NET Framework 4.5, we have exception dispatch info capture throw. And this is the way we rethrow exceptions. This is the only blessed way I'm aware of to rethrow the exceptions. And the important thing is this was changed so many times that it may be that in .NET 10, 11, 12, 15, the throw will work actually properly. So maybe one day this, or maybe even today, this slide is obsolete, but I'm just recommending always go with exception dispatch info. Okay, that would be it with one thingy that we close with one remark. When it comes to finally, we claim that finally should be executed no matter what, right? This is what we typically think about finally. Obviously, if we plug the plug, you know, then nothing's gonna execute, right? But it's kind of logical, right? The thing is, there's so many other cases when finally is not executed at all. It may not be executed when application dies. That should be rather obvious. If you go with task kill the process, it's gonna die, no finallys at all. This makes sense. However, it may be skipped when application exits. So if you call environment exit, your finallys may not be executed. And this becomes a problem. Why? Because you may be releasing native resources in finally, especially in dispose, right? That's the whole point of dispose, to release like global mutexes or things that are managed by operating system and owned by other processes as well. So if we do not call finally, then for instance, the operating system will simply take all the mutexes we have, call them available now, but actually they will be abandoned. So we have no idea whether the memory they are protecting is consistent or not. So this is actually a problem. Another thingy, finally may not be called depending on the exception type you have. Now, if you are really nasty and call some crazy methods, then you get something like execution engine exception or access violation. Actually, there are different flavors of access violation. Some of those exceptions may not trigger any finally blocks, so finally won't be executed. And also may be skipped on unhandled exceptions. This is what I already mentioned. This is allowed by the C# specification. So whenever you start a new thread, always put try catch on it, or generally have try catch everywhere. Otherwise, your finallys may not be executed. However, finally may swallow exception, as we already saw. And general remark, it's not only about C#, but also about other languages. Never return in finally, never throw exceptions in finally. That's kind of asking for troubles. And filtering exceptions, it's prone to the same issue. So if you use this filter syntax or the when syntax for C# exception filters, generally it may break. So be careful with finallys and always make sure that you have your exceptions handled properly, especially when we are talking about rethrowing exceptions and the using construct. And because we have only 3 minutes left, that would be basically it. So if you do happen to have any questions, now is the right time to ask them. At the very end of this slide deck, there are references to a couple of things. For instance, the LSP white paper that I recommend you take a look and read. And also, I encourage you to take a look at my blog, rate this session, etc. And this QR code points to slides. That would be it. If you happen to have any questions, I'm happy to take them. Okay, thank you so much, folks. Enjoy the rest of your day.